So in this previous example, we looked at balancing the reaction of chromate converting to chromium 3+, so being reduced, and N2O being oxidized to NO. In this specific case, we were assuming we were working under acidic conditions, so we balanced hydrogen and oxygen by adding water and protons. Now we're going to look at an example where we're working under basic conditions, but we're going to start out using the same process that we used in the acidic solution. So the reaction we'll look at is the reaction of ferrous hydroxide with lead hydroxide to form ferric hydroxide and lead solid. So just as we did in the previous cases, we want to start by dividing the reaction into half reactions. So we do this by determining the oxidation numbers on each of the atoms in order to decide what's being oxidized and what's being reduced. So if we start by looking at the iron-containing species, we're starting with ferrous hydroxide, and we're going to assume that the hydroxide part is not being redox active. And so in order for charges to balance, we must have an iron 2+ ion to begin with. And then in the ferric hydroxide, we would have an iron 3 ion. So we have iron 2+ being converted to iron 3+, so our oxidation half reaction must be ferrous hydroxide being converted to ferric hydroxide. So now we want to confirm that the other half reaction is indeed a reduction reaction. And so if we look at the lead hydroxide, we have 3 hydroxides and a negative charge overall. So that means we must be starting with a lead 2+. And in the products, we just have lead solid, which would be lead 0. And so that means our reduction half reaction must be lead hydroxide being converted to lead metal. So now that we have our 2 half reactions, we want to balance any atoms other than hydrogen and oxygen, which is actually done for us already. So the iron atoms balance in the oxidation and the lead atoms balance in the reduction. So next we want to balance oxygen atoms, and we'll do this again by adding water. So in the oxidation half reaction, we're starting with 2 oxygen atoms in the reactants. In the products, we're starting with 3 oxygen atoms. So to balance out oxygen, we would add water to the reactant side. In the reduction half reaction, we're starting with 3 oxygens in the reactants and none in the products, so we would have to add 3 waters to our products. So now we've balanced out the oxygen atoms, but in doing so we've added additional hydrogen, and so in this case we're going to again add protons to the reaction. Now we are working under basic conditions, but we're going to correct for this later. So for right now we're going to start out assuming that we're under acidic conditions and add protons. So that means that in the reactants of the oxidation reaction we have 4 hydrogens, and in the products we have 3. So we would have to add 1 proton to the products. And then in the reduction half reaction, we're starting with 3 hydrogens in the reactants and 6 in the products. So we would have to add 3 protons to the reactions. So now we have all of our atoms balanced, and now we want to balance charge. So we want the charge in the reactants to be equal to the charge in the products. And so we'll balance charge again by adding electrons. So in our oxidation half reaction, we have a neutral charge in the reactants and a +1 charge due to the 1 proton in our products. So to balance the charge, we would add 1 electron to the products, making both sides neutral. In the reduction half reaction, we're starting with 3 protons and the negatively charged lead hydroxide. So we have a 2+ charge overall in the reactants, and we have neutral charge in the products. And so to balance out those charges, we would add 2 electrons to the reactants of the reduction reaction. So both sides are once again neutral. So now we want to be able to add the 2 equations together to attempt to get our overall balanced equation. And so to do this, we need to have the number of electrons transferred in the oxidation step equal to the number in the reduction step. Right now they're not, but we can get them to be equal if we were to multiply the oxidation half reaction by 2. So we want to have the gain of electrons be equal to the loss of electrons. So we multiply the oxidation half reaction by 2, and this gives us these 2 overall balanced equations where the number of electrons transferred is equal. So now we want to add the 2 half reactions and cancel any species that occur on both sides. So we have 2 waters in the reactants of our oxidation and 3 in the products, so we'd end up with 1 water in the products. We have 3 protons in the reactants of our reduction and 2 in the products of our oxidation, so we'd end up with just 1 proton in the reactants. And then our electrons are also going to cancel. So with those cancellations taken into account, we have this overall balanced equation. So right now the reaction is balanced overall in terms of both charge and atoms, but the only problem is that we're assuming we're working under basic conditions, but if we're under basic conditions, we won't have an appreciable concentration of protons. So this is where we have to make the correction for the fact that we had been working as though we were under acidic conditions, but we're actually under basic conditions. And so we're going to make this correction by adding hydroxide. So anywhere that we see a proton, we're going to add that many hydroxides to the reaction on both sides. So in this case, we have one proton in the reactants, so we would need to add a hydroxide to the reactant side, but then also one hydroxide to the product side so that we're not increasing the total charge. Now, if we were to add hydroxide to a solution of hydronium, we know that a neutralization reaction will occur and water will be formed. So we're going to assume the same thing happens in this case. So if we're adding hydroxide to a proton, we're going to assume that water is formed. And so the neutralization reaction occurs and we end up with one water molecule in our reactants. So now we've taken into account the fact that we're working under basic conditions rather than acidic conditions, and so that's why we added hydroxide to both sides, and then we performed a neutralization reaction between the protons and hydroxide. So now we can write our overall balanced equation, but first we need to cancel any water that's on both sides of the reactants. So we just increase the number of waters in the reactants to 1, and we already had 1 water in the products, so those would cancel, and so that would give us our overall balanced equation. So in this case, we knew that we had to balance the equation under basic conditions, but we started by just adding protons as our hydrogen source, as though we were working under acidic conditions. And then once we had the two balanced half reactions, we added them together. And then anywhere that we had a proton, we added hydroxide in order for a neutralization reaction to occur. And so that gave us our overall balanced equation under basic conditions.